just to continue on the theme of composite theory, so we're looking at the failure of a composite. So we have a crack that is running through the matrix of a composite material, and we are concerned with what is going to happen at the interface here. In order to understand that, we have to understand something about what happens at the tip of a crack during a brittle failure of a material. So if we look in more detail at the very tip, we find that here we have what is called, at the very tip, a stress concentration. And you can go on the internet and you can find very nice pictures which are taken in polarized light of the failure of things like perspex, where somebody's cut a notch and then applied a load to it. And you can see running ahead of the crack are these lines which represent the stress. Because you're applying a load here, you're trying to separate those two interfaces, so you're creating a new surface, and all of that load is being concentrated in that region there. And the result of that is that that stress concentration, that load, runs ahead in a pattern, something like that. The exact pattern depends on the material, how homogeneous it is for one thing. And the reason we're getting this failure here, because we might be applying a load that's actually less than the known strength of that material, but that load is being concentrated in that region. So in the localized region, that failure is occurring at that point. And that stress concentration is related to how sharp the crack is. And one of the ways you can stop a material from failing, maybe you've got a sheet of perspex and it's got a crack in it and you don't want that crack to go any further. It's a well-known trick. You drill a hole at the end and then that relieves that stress concentration. So that is no longer a point of failure because you've now increased the radius of that crack tip. So we have running ahead of this crack here, this stress concentration. Now what's going to happen when that stress concentration reaches the interface? What happens depends on how strong the interface is between the fibre, the reinforcement, and the matrix. So if we have a glue here at that interface and we are gluing the matrix to the reinforcement, what happens is that the crack runs all the way through. It doesn't even know if a crack could know anything, that there's a reinforcement there. So that crack will run through, and that leads to what is called catastrophic or brittle failure. However, if we have a weak interface, the crack, we draw the reinforcement, and we draw the crack, and we have the matrix. What is happening now if we have a weak interface is that we open up a new surface here. So that's where the interfacial region is. We've got a weak coupling between the matrix and the reinforcement. So we open up this new region. That takes energy. So we might actually stop the crack completely because the amount of energy that's going into breaking this material, creating new surface, is all absorbed in creating new surface here, and that crack will stop moving. But if the crack keeps going, we end up with that. It's the equivalent of drilling a hole at the end of that crack. So by creating this new surface, by opening up this region at the interface, we've blunted that crack. So that stopped the crack. But if it keeps on going, I will have to move over here, so if you'll follow me in this direction. Sorry, this is a bit untidy. We end up with a situation like this. The crack's been running along there. I'll draw it in a different colour. So this is the crack running through the material. It's diverted. So that's crack diversion. Again, we're creating new surface, which takes energy, which slows down that motion of the crack through the material. This is brittle failure. So the crack just goes straight through the reinforcement, and here we're blunting the crack tip. So these mechanisms give you a tough material, and I will, in the next set of slides, show you the consequences.